Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 18 of the course Stochastic Hydrology. In the last lecture, we went through the RIMA model selection based on the mean square error criterion. In the earlier lecture, we had discussed the model selection based on the maximum likelihood criterion. Essentially what we do is that we select a set of candidate models and then estimate the parameters using the calibration data. The first part of the data we use the parameter estimation methods, typically the Marquard's algorithm or the algorithm that is available in MATLAB, and then estimate all the parameters of the candidate models, and then corresponding to each of the candidate models, for the validation data, we compute the likelihood values in the maximum likelihood case, and in the mean square error case, we calculate the mean square error when the model is applied for the validation period. We choose that particular model in the case of forecasting, that particular model which results in the minimum mean square error, and in the case of long term synthetic generation of the data, we choose that particular model which results in the maximum likelihood. Then in the last lecture, we also discussed the procedure for model testing and validation. Essentially, if you recall, we do all these tests on the residues or the residuals that arise out of application of the model on the validation data. You have built the model and apply that model for the validation period. Because you have the data for the validation period, you obtain the residuals as differences between the actual data, actual observed data and the model simulated data, that gives you the residuals. So, you get a residual sequence for the length of the validation period, and that residual series you examine for the major assumptions that we have made in building the model, namely that the residuals have a 0 mean, and therefore, we test for the significance of the residual mean. If the residual mean is significant, then it fails the test. If the residual mean is not significant, that means that it can be approximated to be 0, and therefore, it passes the test. Similarly, we examined two tests for periodicities, one by defining a particular statistic where it examines the periodicities one at a time. So, you form the statistic and then compare it with the associated f value to examine whether that particular periodicity is significant or not. So, like this one by one you test the periodicities. We also discussed the cumulative periodogram test, which is also called as the Bartlett's test for significance of periodicities, where we formulate the cumulative periodogram and then draw the confidence bands, 95% or 99% confidence bands around the cumulative periodogram. If the cumulative periodogram resulting from the residual series lies within this band, significance band, then the series passes the test, in the sense that the series does not have any significant periodicities present in the series. The last series of tests was on examining whether the series is in fact uncorrelated or it forms a white noise, for which we examined two tests. We discussed two tests, one is the Whittle's test and the Portmanteau test, both of which define a particular statistic, and this statistic, if you recall, is dependent on the covariance matrix. What we will do in today's lecture is that we will see how a model is actually applied to several case studies and how we carry out these tests and so on. In the last lecture, I could not discuss any numerical examples. So, today we will see what we mean by one time step forecasting, how do we apply these models in the one time step forecasting, and how we select the models for long term synthetic generation of the data. And then we will also discuss, primarily in today's lecture, I will discuss certain case studies of actual observed data, how we apply that observed data for model building. Now, for the data generation, remember the data generation, we are talking about long sequences of data generated based on the models that we have built on the historical data. So, let us say that we have a AR1 model, that is autoregressive model of order 1. We write this as x t is equal to phi 1 x t minus 1 plus E t. So, let us take one simple example where I fix up phi 1 as 0.5. We will see how we apply this model. So, I will write this as x t is equal to 0.5 x t minus 1 plus E t. Now, E t is a series which has a 0 mean and the series is uncorrelated. So, to apply this, we choose the E t's such that they have 0 mean and they are all uncorrelated. For example, if you take the standard normal deviates, they all have 0 mean and coming from a purely random sequence, they are uncorrelated. So, we choose the E t sequence following these two. Then let us say how do we apply then? To start the generation process, as we did in the Thomas Fairing model case, we start the generation process by assuming an initial value. Let us say x 1 is equal to 3.0. Typically, this is assumed to be the mean of the series itself. Then x 2 I write as 0.5 into x t minus 1, which is x 1 in this case, plus the E t term. Now, these E t terms I may be choosing from the standard normal deviates. So, 0.335. So, I get x 2 as 1.835. Then I will use this 1.835 in the generation of the next value. Phi remains the same, x 2 now when I am generating x 3, and then I put another E t value from the same sequence of random terms, random numbers. I get 2.14, this 2.14 I use to generate x 4 and so on. So, this is how we use the AR1 model to generate numbers, generate the particular variable values. X 1 we assumed and x 2, x 3 etcetera, these are generated. Let us take an ARMA model, that is autoregressive moving average model of order 1, 1, which means it has one AR parameter and one MA parameter. So, x t is equal to phi 1 x t minus 1, this is the AR parameter, plus theta 1 E t minus 1 plus E t. This is the ARMA 1 model. Let us say phi 1 is equal to 0.5 and theta 1 is equal to 0.4. So, this is now written as x t is equal to 0.5 x t minus 1 plus 0.4 E t minus 1 plus E t. When we are doing the model testing, let us say this is our model that we have built. When we are doing the model testing, we use this E t minus 1 as the E t that is used in the previous term, that is for t minus 1. I will explain what I mean by that. Let us say we start with the same value x 1 is equal to 3.0. So, I get x 2 is equal to phi 1 into x t minus 1, which is phi 1 into x 1 plus theta 1 into E t minus 1. To begin with, we assume E t there is no E t minus 1 here, therefore, it is 0 plus E t. Now, this is the E t term that I am choosing, which choosing from a set of numbers which have 0 mean and they are all uncorrelated. So, this is 0.667, I get 2.167. When I go to x 3 to generate x 3, I write phi 1 into x t minus 1, which is x 2, which is this 2.167 plus theta 1 0.4 into E t minus 1. E t minus 1 is the random term that you have used in the previous in generating the previous value. So, that becomes 0.667 plus E t. Now, E t is a new number drawn from the same sequence of random numbers, and like this it keeps on going. So, you generate several values of several values in the series x 1, x 2, x 3, x 4 and so on. So, this is how we do the long term synthetic generation of the data using the ARIMA models. Remember here I have talked about AR and MA. I is the order of differencing which we do before we build the ARMA model. Now, let us say we want to use the ARMA model that we have chosen for one time step ahead forecasting. That is, we chose the model from among us set of candidate models by computing the mean square error of those models, and then finally, we chose this particular model. Now, as I mentioned in the last lecture, what do we mean by forecasting? One time step ahead forecasting indicates that we are in a particular time period and then we want to forecast what is likely to be the value of that particular variable for the next time period. Let us say at the end of the June month, we know the data that has actually occurred for the June month. Now, we want to forecast what is likely, if we are talking about the stream flows, what is the likely stream flow during the next time period, which is July, if we are talking about the monthly time series. So, that is the problem here. Now, when we are talking about the forecast, we are just looking at the expected value of that particular variable during the next time period arising from this particular model. So, if we take the expected value of x t phi 1 e expected value of x t minus 1 plus expected value of E t. Now, expected value of E t is the mean of E t, which is 0, because that is how we have used it in the model, and therefore, I can write the forecast which is typically written as x t cap for the variable x t is equal to phi 1 x t minus 1. Now, if we want to do the same thing for ARMA 1 model, x t is equal to phi 1 x t minus 1 plus theta 1 E t minus 1 plus E t. Remember, this E t minus 1 is coming from the model application for the time period t minus 1, which is a known value now. E t minus 1 is a known value, which was responsible for generating the previous value. So, expected value of x t is equal to phi 1 x t minus 1 plus theta 1 E t minus 1 plus 0. This sequence has a 0 mean, therefore, I write it as 0. So, this is the error in forecast in the previous time period. So, you had applied this in the previous time period, compared it with the actual data for the validation period, and then you obtain this E t minus 1. So, and therefore, that is a known value, and when you take the expected value of a constant, if you recall, it will be the constant itself. Let us say, for example, phi 1 is equal to 0.5 and theta 1 is equal to 0.4 as we considered earlier. We write this as x t is equal to 0.5 x t minus 1 plus 0.4 E t minus 1. For the forecasting, when we are applying it for the validation period, let us say x 1 is equal to 3.0 and I want to forecast the x 2 value. I write it as x 2 cap using that value that model, which is phi 1 which is 0.5 into x 1 3.0 plus theta 1 0.4 and E t minus 1, which is 0. So, that will be equal to 1.5. Now, look at what we do for the second value. X 2 is 2.8, this is the observed value this is not the forecasted value, this is observed or it is the data, and this is the forecasted value. So, we compute the error E 2 as observed minus the forecasted, which will be 1.3, and this is what goes into generating the next value. So, in forecasting the next value. So, x 3 cap I write again as phi 1 x 2 plus theta 1 E 2, and E 2 is 1.3 here. Now, when we are doing x 2, remember you take the observed value. So, you take the actual observed value for forecasting the next one. So, essentially as I mentioned in the last lecture, essentially what we are doing is, in this particular case we are standing in time period t is equal to 2 and then forecasting for t is equal to 3. Now, this is x t, that is x 3 cap, and x 2 is known. So, we obtain the error based on the forecast for the time period to use that error in generating the next value for x 3, next forecast for x 3, that is 1.3. This is what we are using. This 2.8 is the observed value. Like this we keep going. Now, x 3 again we compute the error based on the actual observed value of x 3 and then generate x 4 and so on. So, x 3 is 1.8, this is again the observed value, x 3 cap is the forecasted value. So, we get the error as minus 0.12, this minus 0.12 is what we use in the forecasting of the next value and so on. So, this is how we obtain the forecast based on the ARMA models. Now, what we will do is, we know how to generate the values and we know how to forecast the values, one time step ahead forecasting. I keep on mentioning that they are one time step ahead forecasting models, but you can also have 2 time step ahead forecasting model, 3 time step ahead forecasting models and so on. The difference there would be, in one time step ahead forecasting model, what did we do? We forecasted x t based on x t minus 1, which means standing at the end of the time period t minus 1, we are forecasting x t. Let us say you want to use 2 values, 2 previous values. Typically, in hydrology we do not deal with such situations, but in many of the other areas of engineering, typically they use several of these time lagged values for forecasting. Of course, when I say that in monthly time series forecasting and so on, we may consider previous lags x t minus 3, x t minus 4 and so on. When I discuss the case studies, I will make that more clear. So, in 2 time step ahead forecasting, what we do is, standing at x t, that is we want to forecast x t based not only on x t minus 1, but also on x t minus 2. So, we want to forecast in 2 time step ahead forecasting. I am sorry, I will just explain that correctly. One time step ahead forecasting we did from t to t plus 1, let us say. So, we obtained up to t, it is known, and you are forecasting here for one time step ahead. So, this known data we use in the 2 time step ahead forecasting. Up to this point the whole history is known, we use all of that to forecast not only t plus 1, but also t plus 2. So, this is 2 time step ahead forecasting. Let us say that you are talking about forecasting of a flow increase in a particular river. So, standing in particular time period, let us say 1 hour you are standing a particular hour, then you would like to say that the next hour the level will be so much, the hour next to that the level will be so much. In the case of flows, standing in June month, you may want to say what is the forecast for July and what is the forecast for August based on these models. Now, when we are applying it for 2 time step ahead forecast, the assumption is that you have the observed values only up to this time period t. So, using this forecast you have forecasted x t plus 1 cap. Now, when we are forecasting for x t plus 2, you use the forecasted value for x t plus 1, namely the x t plus 1 cap that you use, because you do not have, when you are doing 2 time step ahead forecasting, both these 2 time step ahead actual values will be available only at the end of this 2 time steps. So, when you are doing 2 time step ahead forecasting, in obtaining your errors here, you will use the forecasted values, because you are doing 2 time step ahead. The values will be known only when you reach the end of time period t plus 2. Anyway, this we will discuss further when we look at some applications. Now, what we will do is that the main time series analysis procedures that we have studied so far, namely that the correlogram, correlogram gives us certain information, the partial autocorrelation function gives us certain information, the power spectrum gives us certain information. All of these information, all of this available information from the historical data, we synthesize and build the models. Once we build the models, we validate the models based on the residual series. Now, these several steps we will apply to several case studies, several different case studies. In certain case studies, I may only discuss correlogram and spectral analysis and so on. In certain case studies, we will go all the way up to building the ARMA models and see how they can be applied for actual data generation as well as forecasting. Now, you must remember, I have kept on telling in this course that the daily rainfall data behaves much differently from, let us say, a much normalized, much smoothened process like a monthly stream flow or seasonal stream flow and so on. Let us look at first the daily rainfall data, and we consider this daily rainfall data for Bangalore city for certain duration, and we plot for this daily data, we plot the time series, autocorrelation function, serial partial autocorrelation function and power spectrum. Then what we will do is, we will add the daily data to obtain the monthly data and do the same analysis, see how they appear differently, they appear different from each other, and then add all the monthly data and obtain the yearly data and look at how the yearly data looks compared to the daily data. What we may expect in an urban area, the rainfall, daily rainfall is, in some sense it indicates a random process. I mean, the number rainfall data may be uncorrelated, and you may not get any significant periodicities if you are looking at short duration rainfalls such as daily rainfall. And in fact, these short duration rainfalls are what cause the urban flooding, and therefore, it is important to understand how the rainfall process itself is behaving. So, let us look at the time series. Certain length of the data I have taken and then plotted the time series. Now, this is how the time series looks like. There are a large number of zeros here, and then from the time series, you can't make out much in this daily case. If you go to monthly or yearly cases, we may perhaps suspect that there is some periodicity, but when we are talking about rainfall and you are plotting for a short time duration such as a day, it is very difficult to understand whether there are any significant periodicities present in the data and so on. So, we will plot the correlogram. Now, when I plot the correlogram, as you can see, these are the significance bands here, that is 95% significance bands. Most of the correlations with respect to most of the lags, that is correlations with respect to most of the lags, are within the significance bands, indicating that they are all insignificant. There are hardly few initial lag correlations significant, and there may be some of these which are significant at perhaps regular intervals. We will have to check this with the spectral analysis. So, this indicates that the daily rainfall data is likely to be uncorrelated, although there are certain significant periodicities. For example, we are not getting a peak like this 0.15, 0.2 and so on, except for lag 0, which is lag 1 perhaps near to 0, which is close to 0.15. This value is not exactly for lag 0 correlation is always 1. Now, we will see what happens when you have when you look at the partial autocorrelation. Again, partial autocorrelation, this is a significance band here. Remember, I mentioned during the discussion on partial autocorrelation that being a autocorrelation, its significance bands will also be same as the significance bands for the correlation, which is in this case we take it as plus minus 2 by root n being the data, n being the length of the data. I am sorry, n being the number of data points. So, most of the partial autocorrelations also are insignificant, except for the very first few, maybe first one, second one and so on. Then we will look at the power spectrum. So, power spectrum, if you had regular periodicities, what you would have seen that most of these spectral values will all be in certain band, and suddenly you see a large spike, but that you are not seeing it in this particular case. It indicates that there is a important contribution to variance somewhere around this point, maybe around just less than 0.1 and so on, but by and large it is spread. There is no significant value around which there is a contribution to variance. So, the daily data typically behave like this, daily rainfall data typically behave like this, where you are unable to say much on what kind of regularity exists in the data, what kind of deterministic component you can extract from the data and so on. Obviously, because this is all typically you find uncorrelated values of rainfall, and when you are talking about smaller durations of daily rainfall or 6 hourly rainfall etcetera, which are important in the flooding situations, it is extremely difficult to get a good deterministic component. They behave mostly like purely random processes. Let us now add up all the monthly daily values and generate a monthly time series. So, in this case we have about 32 years of data, and this is a monthly time series. Now, the monthly time series appears to tell us that you may suspect certain periodicities. There seems to be certain regularity here in terms of the fluctuations, and this one becomes more clear when this information that we are suspecting the time series to hold becomes much more prominent when we do the correlation or the correlogram analysis. So, in the correlogram you see a sinusoidal variation. Remember, between this and this, notice that between this and this there are 20 values. So, it is going like this, there is a sinusoidal variation like this, it keeps going on like this, and then there is a slow decay as you progress into time. We are going up to about 195 or something, some lag. There is a slow decay of the correlations. These bounds are again the significance bounds, 95% significance bound, and most of the correlations are significant, as you can see. Now, this typically indicates that there is a periodicity present in the data. For example, this may correspond to 6 this may correspond to 12 and so on. We will see what exactly it means when we look at the spectral analysis. So, the correlogram for the monthly data definitely indicates a presence of periodicity. The correlogram is dying down in a sinusoidal form. Compare this with what we did for the daily. See, this was the daily data correlogram, where most of the correlations were insignificant, whereas when you come to the monthly data, most of the correlations are significant, and then there is also a sinusoidal variation indicating that there is a periodicity present in the data. Now, we will see how the partial autocorrelations show up. The partial autocorrelations, there are many significant partial autocorrelations, as you can see, the corresponding to 1 perhaps there is a significant partial autocorrelation, these are significant and so on. As you go further, however, most of the partial autocorrelations become insignificant. This is for the monthly data. Now, what does this tell in terms of our model building that we have discussed earlier, that if your autocorrelogram or the correlogram indicates that there is a sinusoidal or exponential decay, and there are certain partial autocorrelations which are significant. This indicates a MA model, MA process, in which you can use these significant partial autocorrelations to build the MA model. However, we are not adopting that procedure, that procedure of identification, as I mentioned. We simply build candidate models based on this information and then look at the particular models to be chosen. I am sorry, I just want to correct that. When you have the autocorrelations decaying slowly with respect to time, and there are certain partial autocorrelations significant, it indicates a AR process, not the MA process, it indicates a AR process, and then the order of the AR autoregression we choose based on the number of partial autocorrelations which are significant. Okay. Now, we look at, for the monthly data, we look at the power spectrum. See, this indicated the correlogram indicated that there is a certain periodicity, and we also suspected that there may be a periodicity corresponding to 6 months, there may be periodicity corresponding to 12 months and so on. So, this information is strengthened, this indication is strengthened by the power spectrum. When I plot the power spectrum, I get a periodicity corresponding to somewhere around 0.52 or something, then 1.23 and so on. So, this corresponds to, if we use W k is equal to 2 pi by p and associated W k value if we put, this corresponds to a periodicity of 12 months, this 6 months, 4 months and so on. So, in the monthly data for Bangalore city, we observe that there is a periodicity of 12 months, which is in monsoon situation it is quite common, where there is a regularity in the rainfall patterns. But these are not so intuitively clear, that why there should be a 4-month periodicity, why there should be a 6-month periodicity and so on. And as I mentioned earlier, while the spectral analysis brings out the fact that there are certain periodicities present in the data, whether these periodicities are in fact significant or not, we need to test separately. So, this information only indicates that there is a 12-month periodicity, 6-month periodicity and 4-month periodicity here. How do we obtain that? That is simply by p is equal to 2 pi by W k, and the W k is associated with that particular spike. You pick up the W k associated with this and then get the periodicity. Now, we will go one step ahead now. So, we started with the daily data, we did all this analysis, we could not get much of the information out of that. Then we added all the daily data, obtained the monthly data and did the analysis for the monthly data. The monthly data correlogram showed up, periodicity is present in the data, and that was fortified by the power spectrum. Now, we will add all the monthly data for the 12 periods in the year, 12 months in the year, and then formulate a yearly time series and plot the time series. So, yearly time series if you draw, this is between 0 to about 1400 millimeters annual rainfall in Bangalore city. If you plot that, this looks slightly haphazard like this. So, the time series for last about 32 years or something we have taken here, and this is how it varies. Let us see what happens to the correlogram of this, correlogram of the annual data. Now, the significance bands are here now. Why are the significance bands different from monthly to daily to annual? It is because of the number of values that you are using. This is 2 by root n, and n in the case of monthly time period is let us say it is you have annual data and 1 year consists of 12 months, and therefore, the number of months will be much larger than the number of years, and therefore, the number of values that you use to compute this for the annual data will be much smaller than the number of values that you used for monthly data, and this is 2 by root n, and therefore, as n increases, as n decreases, this will be larger and larger. So, you are getting a larger and larger insignificance band, which means that if the correlations lie within this band, then they are all insignificant. So, as you can see, all the correlations for the annual rainfall data, they are all insignificant, statistically insignificant. We leave out the lag 0 correlation because that is always 1. So, all other remaining correlations are all insignificant. Let us look at what the partial autocorrelations say. Partial autocorrelations also bring up the same conclusion that all the partial autocorrelations, most of the autocorrelations except this and this here somewhere around lag 10 and lag 9, they are significant, and then lag 5 is significant, 0 you leave out, and this is what the partial autocorrelation function brings up. So, as we progress from daily to monthly to annual, the behavior of the process changes, and this is important in hydrology because what you are applying the models for, is it the daily forecasting that you are looking for, is it the monthly time forecasting and so on. So, depending on that, the information content in the time series is much different. The power spectrum, look at the power spectrum. Now, compare this with what we had, this is for the annual data, compare this with what we had for the monthly data. Monthly data showed definite periodicities present in the data, and the daily data showed that power spectrum more or less behaves like a like it is for a white noise. Now, here there are some lower frequencies and some higher frequencies that are dominant. So, you cannot say much about the time series from the power spectrum data alone. Now, we will go to a much more smoothened process of stream flow data, and we will consider the annual stream flow data. There may be certain trends in the annual stream flow data. Let us say the stream flow data may be increasing or decreasing slowly and so on. This information on the trend, existing trend, is important for water resource managers to use for planning for the next 10 years, 15 years and so on. But apart from the trend itself, we would like to build models for synthetic generation of data as well as for forecasting of the data. So, let us look at annual stream flow data. So, this is for 60 years at a particular location. There is a certain trend, on an average these are all increasing. So, there is a increasing trend for over the last about 60 years. These are in Qmax. So, this is the discharge value with respect to time in years. Now, we will plot the correlogram for this. I have gone up to about 30, but which is actually 50% of the data available, but typically we go up to about 15% of the data available. So, if you plot the correlogram indicates a exponential decay here. As you are progressing with respect to time, there is an exponential decay on the correlogram. This is the annual stream flow data. Then we look at the partial autocorrelations. So, we plotted the time series, we plotted the correlogram indicates that there is a exponential decay in the correlogram. Now, we look at what is the partial autocorrelation. What does the partial autocorrelation say? If you see that there is a decay in the correlogram and there are certain partial autocorrelations significant, you can suspect it to be a AR process, autoregressive process. So, let us look at the partial autocorrelation. There are at lag 2, the partial autocorrelation is 1, nearly 1 here, and then at lag 3 also it is significant, and then there are no significant partial autocorrelations. This is just coming up out, these two are just above the significance bands. But typically you can say that 1 and 2, lag 1 and 2 are significant. So, you may suspect this to be an AR2 process. Now, we look at the power spectrum. The power spectrum indicates for this particular case study that the lower frequencies dominate. And when I discussed examples of theoretical AR models, typically this is what we brought out, that the power spectrum for one AR2 model you may have lower frequencies dominating, for some other AR2 model you may have middle level frequencies dominating and so on. But typically it is a correlogram and the partial autocorrelation function. These will indicate, these will give good indications for the autoregressive process. So, in this particular case we can say that this follows closely the AR2 process. Now, what we do is, because we saw a trend here, the time series had a trend, we want to remove the trend. So, what is the procedure? In the ARMA model procedure that we adopt to remove the deterministic components, we do the differencing first. So, x t minus 1, that is the first differencing. So, let us see on this, if we do the differencing, we get the time series for the first difference data, that is first order difference data. As you can see here, what was appearing like this in the original time series, now when we do the differencing it appears something like this, which means that the trend that was so apparent in the time series has been removed now. We will do the correlogram analysis on this time series now. When we do that, the correlogram for the first difference data, you can see that there is only one correlation, the lag 1 correlation, that is significant, and unlike what you saw in the earlier case where there were several correlations significant, these were, as you can see, almost up to lag of about 12, they are all significant. Although they are decreasing with lag, they are all significant. Whereas, for the difference data you see only lag 1 correlation coming up as significant. The partial autocorrelations again indicate that most of the partial autocorrelations are insignificant. There is one at a very high lag that you can ignore when you are building the models, and there is one at the beginning of the series, which is maybe around lag 2 or something, it is significant. So, by differencing, essentially you change the nature of the information content in the data. One, you remove the trend, because you removed the trend, the correlogram behaved in a different fashion, the partial autocorrelation function behaved in a different fashion. And now, look at the power spectrum. Power spectrum for the difference data, it indicates, unlike your power spectrum of your original data, which had significant contribution to various variance in the lower frequencies, this is slightly more distributed now. So, you have frequencies, you have variation contribution to variance almost up to about 1.2 or something, Wk up to about 1.2. Now, what we will do is we will look at some case studies on ARMA models. So, both the case studies that I just discussed were with respect to only getting the information content from the time series plot, from the correlogram plot, partial autocorrelation function plot and the power spectrum plot. So, we just visually look at this, we prepare all these plots and then visually look at this and then try to get the best information that is possible from these plots. Now, we will do the actual model building exercise, where starting with the observed data, we select certain candidate models and then obtain the parameters, obtain the residual series, that is for the calibration period we obtain the parameters, and then for the validation period we obtain the residual sequence, and then we do the tests for the residual series to examine or to ascertain whether the model that we choose, either based on the maximum likelihood criterion or the minimum mean square error criterion, in fact passes the tests, all the 3 tests that I indicated earlier. So, we will take the monthly stream flow data for Kaveri river at Krishnaraj Sagar in Mysore. So, this is monthly stream flow data, this is cubic meters per second. The data is available for 1934 to 1974. We will plot the time series, we will plot the autocorrelation function, partial autocorrelation function and the power spectrum. Then we see that if there are periodicities present in the data, because we are talking about monthly stream flow data, as I have been saying repeatedly that the monthly stream flow data are almost certain to show up monthly periodicities, I am sorry, periodicities corresponding to 12 months, especially in the monsoon regions like ours. So, the time series of the data we plot all of this, then once the periodicity is indicated, let us see how we can remove the periodicities. So, in this particular case we simply standardize the series, obtain another series by standardizing and then look at whether the periodicities are present or not. So, that is the exercise we do now. So, this is the original time series, there are 480 values here, that is about 24 years of data. So, you have the monthly stream flow data. As you can see, there is a regular pattern here. So, you can suspect that there seems to be some periodicities present here. Then we plot the correlogram as was shown for the previous example. The correlogram shows a sinusoidal oscillation like this, and large number of correlations are all significant. We have gone up to about 230 or 240. We had 480 values. So, we have gone up to 240 n by 2, and there is a slow decay here, but the decay is rather slow because we have gone up to 240 and then they are still significant. So, this shows that there is a significant periodicity indicated by the correlogram. Now, let us look at what do the partial autocorrelations say. The partial autocorrelations also are significant at several lags, especially towards the end, but if you leave out these farther points, there are significant partial autocorrelations at the initial locations. Even these are significant, but there are somewhere around, let us say 8, 10 etcetera, these are quite significant here. Then we do the power spectrum. The power spectrum, much like the power spectrum that we considered in the stream flow case that I discussed in case 2, these show up, I am sorry, in the case 1 where we added up the monthly rainfall data, these show up significant periodicities, and this periodicity corresponds to 12 months, this to 6 months, 4 months, 3 months and 2 months. So, these periodicities in the monthly data are indicated by the power spectrum. Now, what we do is we want to remove the periodicities. We do not even examine whether these periodicities are significant or not. We have observed that there are periodicities present in the data, I just want to remove the periodicities. We could have tested with first order differencing, second order differencing, etcetera, whether any effect is there by the differencing on the periodicities. But what we do is we directly go to standardization. Let us see whether the standardization removes the periodicities. So, I do the standardization. How do I do the standardization? If you recall, we simply take this is for the standardized data. So, this is Z t is equal to x t minus x I bar by S I. This is how I obtain the standardized series. Now, x I bar is the mean of the month to which the time period t belongs, and S I is the associated standard deviation. So, that is how we standardize the data and then plot the standardized data. By the data alone, we will not be able to say much here from the standardized data, except that this looks much different from your original data. Original data did show up some regularity, and that regularity is not seen in the standardized data. But we will plot the correlogram, that will give us much better information. As we plot the correlogram, as you can see here, the original data showed up a regular sinusoidal decay in the correlogram, whereas that kind of behavior is completely absent in the correlogram of the standardized data. So, by standardization you have removed much of the periodicities, but this we can ascertain by plotting the power spectrum. The partial autocorrelation function, again most of the partial autocorrelations become insignificant, and there are certain partial autocorrelations which are significant towards the end of this. However, we are not yet at the stage of model building. So, we will not consider this information at present, but let us look at power spectrum, because our aim was to examine whether by standardization we are in fact able to remove the periodicities or not. So, the power spectrum here shows that most of the periodicities are all removed, because you are seeing that there is no significant spike here, which indicates that there is a major contribution to variance at that particular point. So, the power spectrum more or less shows that the variance is uniformly distributed, more or less uniformly distributed across all the frequencies. So, what we now do is that we have removed the periodicities, but there are certain correlations present in the data. There are certain significant correlations present in the data. We use now the standardized series and use the fact that it does not have any significant periodicities present in the data. We will build a model, ARMA model on this data and do all the tests that are prescribed for the data. I repeat here again, the procedure that we are adopting in this particular course is not just the identification, parameter estimation or the calibration and validation, as has been classically described by in the Box-Jenkins type of models. We adopt more or less the procedures prescribed by Kashyap and Rao 1976, the textbook which I have been referring in the last lecture. We adopt that procedure in which we formulate the candidate models. In formulating the candidate models, we use the information provided by the correlogram, information provided by the spectral density and the partial autocorrelations, just to see which of the parameter, which how many of the AR parameters and how many of the MA parameters to be included. So, the partial autocorrelations, autocorrelations and the spectral density together give us some indication on how many of AR terms, how many of MA terms, which of the terms to be included in the non-contiguous models and so on. So, this is the information that we get from the earlier analysis that we have done. Based on these, we form certain number of candidate models. We do not pinpoint to a particular model. We form a number of candidate models, and then associated with each of these candidate models, we obtain the likelihood values and the minimum mean square values. So, this discussion will continue in the next class. So, what we discussed today is essentially how to use the ARMA type of models for one time step ahead forecasting and for long term data generation. And then we examined 3 case studies. In the first case study, we started with daily rainfall data, then we aggregated it to monthly rainfall data, and then considered also the annual rainfall data. Then we saw the different information content in the information content in these different series, daily series, monthly series and the annual series. And then we considered also a monthly stream flow data. Before that, we considered the annual stream flow data, which showed a trend, and by first order differencing we showed how the trend has been removed from that particular data. Remember, these are all actual case studies where we are using actual observed data. The first one was for Bangalore rainfall data. The second case study is from a US site. The data has been downloaded from US site, but the analysis has been done by my own students here. And then the third case study was for the Kaveri river data. So, we have considered the actual observed data and then made these analysis to see what kind of information is obtained from all of these analysis techniques that we have discussed. Now, in the next class, we go one step ahead and then look at the same case study, the third case study, and see how we build the model, both for long term synthetic data generation as well as for forecasting. Typically, we will also discuss how the residual series are obtained, how we do the tests, statistical tests, how we decide whether the period there is any significant periodicity present in the residual series or not, and so on. So, thank you very much for your attention. We will continue the discussion next time.